Hi,
Hi,
everybody.
hi everyone. Looks like we're live. It's great to see everyone again.
Mhm. Today we'll be doing a live solve for the 2015 AMC 8.
Yeah. And I guess before we can get started, we can introduce each other.
Mhm.
So my co-host is my co-host is my co-host is Angie, and she's actually very good at math. So she's been doing competition math since fifth grade, and she's an Amy qualifier, and also has qualified for Math Count States 3 times and placed fifth at state, which is very impressive. In addition, she also volunteers for a local math camp, plays piano, tennis, and enjoys watching sports.
Yeah, hi, everyone. And with me today is going to be Kevin. And Kevin also has a lot of math competition experience. He actually placed in the top 24 on the USA Junior Math Olympiad. And he is a two-time AMC 10 Distinguished Honor Roll winner. Outside of competition math, he also runs his own nonprofit organization, and he is excited to meet you guys, which is amazing. And it looks like you guys are able to work with the chat relay, and we see a lot of cool messages in the chat. All right. And just as a reminder, to access the problems for today, we're going to go to this link, live.poshenloh.com/past contests AMC8 2015.
Yeah, and I think unless there's something else we need to do, I think we can get started with the problems.
Yeah, let's get started. All right, question number 1. And it reads, how many square yards of red carpet are required to cover a rectangular floor that is 12 feet long and 9 feet wide? So we have this rectangular carpet, which is 12 feet by 9 feet. And our problem is asking us, we want the number of square yards of red carpet on this rectangular floor. And square yards, well, that's not the same as feet, right? How many yards are in, okay, or rather, how many feet are in 1 yard? Type in the chat relay. All right, you guys are all typing in 3, which is great. There are indeed 3 feet in a yard. And so for this problem, we're obviously going to want to convert these dimensions into yards first. So if we do that, 12 feet, since there are 3 feet per yard, how many yards are going to be in 12 feet? And that's going to be 4. Good job, Brian. And similarly, how many yards are in 9 feet? That is going to be 3. Good job, AMC 8. And finally, we're looking for the number of square yards in the entire rectangular carpet. So we're just going to multiply our dimensions. And that's going to be 4 times 3, which is 12 square yards for our answer of A. Not too bad for question number 1.
Yeah, definitely. And now we can move on to question number 2. And this one seems to be a little harder because now we have a regular octagon, A, B, C, D, E, F, G, H. So in this regular octagon, we have that X is going to be the midpoint of side AB. You want to see what fraction of the octagon is going to be shaded. Well, the first thing that we can do to start, looking at this problem is the main difficulty is we don't quite know what to deal with the side AB because X is the midpoint of AB, right? So let's see here. We can see that, this thing sort of looks like half of the octagon, but just a little less because, we're missing this little section here. So if we just extend line XO and we let it hit the other side EF, well, then we just have, exactly half of the octagon since, this is just half the octagon, right? But we're subtracting out this tiny right triangle here. So what percentage of the octagon's area would this right triangle be? Does anyone know? Yeah, that's exactly right, 1/16. And the way we can figure this out is that this right triangle is going to be one half of this larger isosceles triangle. So this right triangle is going to be 1/2 of the area of OEF, and OEF, as we know, is going to be 1/8 the area of the entire octagon. So we know that this area is going to be 1/2 times 1/8 equals 1/16 of the area of the octagon. So our total area is going to be 1/2 of the octagon, like I said before, minus 1/16, which gets us 7/16, which is our final answer. So that one was a bit tricky, but after carefully subtracting areas, we eventually got a final solution.
Awesome. And notice how you don't really need any information about side lengths or really anything other than the area proportions to solve this problem. So let's move on to question number 3. Okay, we have Jack and Jill, the infamous names, and they are going swimming in a pool that is 1 mile from their house. They leave home simultaneously, so they're gonna leave their home. Let me see if I can draw a nice home. This is their home. And they're gonna leave their home at the same time. And Jill rides her bicycle to the pool at a constant speed of 10 miles per hour. So Jill is going to be pool over here, and note that this distance is actually 1 mile. So we are given that Jill is riding her bicycle at a speed of 10 miles per hour. 10 miles per hour. And at the same time, Jack is walking to the pool at a constant speed of 4 miles per hour. So Jack is also walking in the same direction, but at a slower rate. And we're asking, how many minutes before Jack does Jill arrive? So really, we just want the difference between the times it takes for them. So I see RC already has a solution to this problem. So for the first part, as AS says in the chat, it's going to be 60/10 or 6 minutes. And that's because if we have 1 mile over here and we know that Jill is riding at 10 miles per hour, because we only needed one of those 10 miles, we're going to have that the time it takes is going to be 1 hour over 10. But that's also the same as converting to minutes. That's also 60/10 or 6 minutes. And then doing the same thing as you guys have all said in the chat. Okay, whoever is no name has a great expression. So that's going to give us that Jack travels at 4 miles per hour. So every 1 hour, 1/4 of that time gives you 1 mile. So 1/4 of an hour, which is 60/4 or 15 minutes. And then now all we have to do with these numbers is take the difference. No matter what difference, we're going to take the positive difference. So our answer is going to be 9 minutes, which is going to be answer choice D. Also not too bad.
Yeah, starting easy so far, but it looks like it's going to get harder because question number 4 says, the Centerville High School chess team consists of 2 boys and 3 girls. So a photographer wants to take a picture of the team to appear in the local newspaper. She decides to have them sit in a row with the boy at each end and the 3 girls in the middle. How many such arrangements are possible? So let's see here, right? We have 2 boys and 3 girls, and we want to arrange them to be in the local newspaper. So in this case, we can start by just observing that each boy has to be on each end, and the 3 girls have to be in the middle. So we can draw something like this. So this has to be a boy. This has to be a boy, and the 3 girls are in the middle. So let's try to count how many boys there are first. So how many ways are there to arrange the 2 boys in this arrangement? Does anyone know? Yeah, exactly, AMC 10. It's 2. So there's 2 ways to choose, where the first boy sits, if they sit, here or here. And after that, we can see that, we can sit here in 2 ways. We can choose which boy sits there, and there's just 1 way for the other one. And for the girls, well, there's 3 ways to choose where the first girl sits, 2 ways to choose where the second girl sits, and 1 way for the third girl. So in total, there's 2 times 3 times 2, which equals 12 ways total.
Yeah, exactly. This is using the ideas of factorials because there's three girls, so it would be, if you wanted to find all the ways, that's six. But there's also another way, which is using factorials. So the number of ways to arrange n people in a row of n chairs would then be n factorial. But that's just a little bit of an easier example of using factorials. Now let's move on to question number 5. So we have all of these numbers over here. And it looks like what we want to do is basically these are the numbers of the scores of Billy's basketball teams. And we know that his team is going to score a 40 in the 12th game. And out of these options over here, we want to know which statistic will actually increase. So we're going to add an imaginary 40 to this, representing his 12th game. Okay, I already see someone typing in range in the chat, which is good. And so it looks like RC says that there's no numbers smaller than 42. And if we add 40, the range will go from 31 to 33. And that's exactly right. The key thing to realize here is that even though this list, okay, wait, this list is actually in increasing order, which makes our work a lot easier here. A lot of times in AMCs, you won't see them putting the lists in order, but in this case they did, which is very nice of them. And so actually we can move our 40 to the very beginning of the list. So it's going to go over here. And what that tells us is that now 40 is the smallest number in the list. And so I see no name us in the chat. What is mid-range? Well, mid-range, it's actually exactly what it sounds like. It's the middle of the range. In other words, if you were to take the range, which is sum x plus y over 2, with x the smallest, y the greatest number in the set, then x plus y over 2 is the mid-range. Think of it as the mean of the range, or the half of the range. And this is also going to be the very middle number in the set. But if we look through all of these options here, okay, we know for a fact that the range is going to increase because we just added a smaller number in the set. So we can just be done here, but let's go through all of the other numbers first. We know that the median, that's okay. If we add a smaller number to the set, that's going to give us more to the left, which means that the median is going to be shifting to the left or getting smaller. So that's not going to increase. Similarly for the mean, okay, well, you're adding a smaller number in. Because all the other numbers were already greater than 40, we know that the mean had to already been greater by a lot more. But if we add the 40 in, that's going to decrease it. All right, let's look at the mode. Well, okay, there wasn't a 40 already here, so the mode actually doesn't change. So because the mid-range is smaller than the range itself, that's also not going to increase. So clearly all we're left off with is the range, which is answer choice A. And yeah, it's supposed to be mode, not mod, but you guys got the idea. Oh, and it looks like Kevin, we cannot hear you.
Hello, does it work now? Okay,
Yeah,
cool.
we can hear you.
Oh, yeah. So now we can move on to question number 6. And question number 6 says, a geometry problem. In triangle ABC, we have AB equals BC equals 29 and AC equals 42. So what is the area of ABC? Well, the first way to start off any geometry problem is obviously to draw a diagram. So magically, I've just drawn a diagram right now, and now we're ready to solve the problem. Okay, so let's see. So in this problem, basically we want to have AB equals BC equals 29. So let's draw that in first. So 29, 29. And we know that AC is going to be equal to 42. So and since we know that X is going to be the midpoint of AC, so we want to draw in this point X here. as the midpoint of AC. And the reason we want to draw in X is because triangle ABC is isosceles. And what this means is that if we draw in the midpoint X of AC, then this is actually a right angle. That's just the property of isosceles triangles, is that, if we draw the midpoint, it's actually perpendicular with this line. So this line is going to be perpendicular to AC, the base. And so after this, now what we can do is we can say, since AC is 42, we can say AX is going to be 21, and XC is going to be 21. So our final area is going to be 21 times, oh yeah, so our final area, there's actually one more step that we're missing. I almost forgot. We need to use the Pythagorean theorem because we know that AB is 29 and AX is 21, but we want to know what BX is, so we want to figure out the height. So this height is going to be, using the Pythagorean theorem, we can figure out the height as 29 squared. So 29 squared, hello. So we can figure out the height is 29 squared minus 19 squared, or sorry, 21 squared. And using some difference of squares, we can compute this as 29 minus 21, which is 8, times 29 plus 21, which is 50, which equals 400. So the square root of 400 is going to be 20, and our final answer is just the base, which is 21 times 2, times the height, which is 20, divided by 2, which equals 420. And this just shows how important it is to use, always draw in the altitude whenever you see an isosceles triangle.
Yeah, and really in any geometry problem, the very first thing you should do is draw a diagram, as that is going to be very helpful. But next, let's go to the problem number 7, which looks like a probability question. So we have 2 boxes, and each of them has the chips 1, 2, and 3. This is box number 1, this is box number 2. And we know that a chip is randomly drawn from each box. So we're going to take one from this box and one from this box. And the numbers on the 2 chips, whatever we get from here, they're multiplied. So if we got a 1 here and a 1 here, we multiply them to get 1. And we're looking for the probability that their product is going to be even. So there's 2 things we need in every probability question. We need the successful outcomes and we need the total number of outcomes. In this case, there's actually not too many total outcomes. So one thing you can do is try to get some sort of pattern as to how the numbers are going to look like. But one thing to notice is that, okay, if we want to multiply and get an even product, what is that going to consist of? Well, an even number has to be in one of these 2 spots because we always need a multiple of 2 to get to an even number. So there's going to be some even number here, and then any even or odd number here. And then let's just look at how we can get an odd number to multiply. Well, if we had any even number in any of these spots, then this number is automatically going to be even. So that means that for an odd number, we have to multiply 2 odd numbers together. So that inclines me to choose to let's see how many ways we can get an odd number out of these, because there's actually going to be less cases here, and it's going to be easier to calculate. So let's try to do that. So for the successful outcomes, to get an odd number, what are we going to do? Well, the total, we can choose 3 from each box. So there's 3 possibilities from each box. So that means that 3 times 3 is our total. And then to get an odd number, well, we need an odd from both of these. Which numbers are odd in both of these? Well, the only odd numbers are 1 and 3 for both of them. And exactly as William says in the chat, the odd numbers are going to be 2 in each, which means that we multiply by 2 twice to get the possible number of odd combinations. And that is going to be 4/9. But be careful, because in this kind of a situation, we solve for the opposite of what we wanted. So what we want to do here now is subtract this from our total, which is always going to be 1. So our actual probability is 1 minus 4/9, which is 5/9. And this is a very common strategy when you get the odd and even multiples for probability questions, is to think of it in cases. Okay, For an even number, this is what you can do to get there. For an odd, this is what you can do to get there. And think of which case is easier to multiply out. Obviously, they were pretty close, but for me personally, I think that multiplying two odds is a lot easier in this case. And yeah, you can always use a chart, and that works great for smaller problems like earlier in the AMCs. But then when you get into later and there's a lot more cases, it's easier to do these multiplication properties and have a lot less cases to work with. And sometimes you'll have multiplying, sometimes you'll have sums, and then you just have to make some cases for each of those possibilities.
Yeah, absolutely. And we can now move on to question number 8. And question number 8 says, what is the smallest number larger than the perimeter of any triangle with a side length 5 and a side length 19? So this problem is kind of a mouthful. So let's think about how we could approach this. So if we have a triangle of side length 5 and a side length 19, basically what this means is that, so we can think about this. So basically what this means is that we'll have, one side with a side length of 5, one side with a side length 19, and then one mystery side. And we want to basically figure out what this mystery side's length is going to be equal to, or what's the maximum possible value it can be equal to. Because this is a little tricky because you might not be able to think we want to use maximum for this problem, but we actually do, because as the smallest whole number larger than the perimeter of any triangle. So for any triangle, we need to make sure that our side length here, this thing, we can say this is going to be less than or something for any side length. And I actually see a lot of ideas in the chat, but unfortunately, I don't think a lot of them are correct, because you might just think we can just use the Pythagorean theorem in this question, but it's actually not the case. Because if we use the Pythagorean theorem, what we end up getting is that we get x is like probably something less than 20. Yeah, exactly. I think has the right answer. We want to use the triangle inequality. And the triangle inequality tells us that, two sides of a triangle is always going to be greater than the third side. So in this case, so in this case, two sides of the triangle are 5 and 19. So 5 plus 19 is going to be greater than the third side, which is x. So x is going to be less than 24. Now, if we think about the perimeter, which is what we want to figure out, well, then the perimeter is going to be 5 plus 19 plus x, which is equal to 24 plus x. But remember, x can't be equal to or greater than 24. So this has to be less than 24 plus 24, which is 48. And so 48 is going to be our the smallest whole number larger than any perimeter of the triangle. And that's our final answer.
Yep. The key thing for this problem is to use the triangle inequality. And the reason, okay, Pythagorean theorem is not necessarily wrong to use in this case. It's just that it doesn't really maximize or minimize anything for us. Because, okay, if you think about it, you can have an acute triangle, a right triangle, or an obtuse triangle. And if we really want to maximize perimeter, it makes more sense to have the biggest triangle, or like an obtuse triangle. So that's why using Pythagorean theorem isn't necessarily going to give us that maximum amount. But let's move on to the next question. This is going to be question number 9. So in this question, we have Janabelle, who sold 1 widget on the first day of work. On the second day of work, she sold 3 widgets. So this is day 1, she sold 1. Day 2, she sold 3. And then each day after day 3, which she sold 5 on, she's going to sell 2 more every day. So 1, 3, 5, 7, basically all the odd numbers. And so we're looking for how many widgets in total had she sold after 20 working days. So actually, there's a pretty good trick for this problem, but let's just start it off and break it down. So what we do know is that we're basically counting odd numbers. And the first thing we want to find is, well, how many are we really going to be selling on day 20? That's going to be our last amount. If you notice, this is actually an arithmetic series at the end, but let's start with day 20. So notice how every day we're going to be adding 2 more. So plus 2, plus 2. And so it helps us to find some sort of expression that we can use for any general day. So for example, for day 2, we had our original amount of 1, and then we added 2 to it. But what is that 2 really doing? Well, let's move on to day 3. We first had our 1, but instead of just adding 1 2, we added 2. And notice how that's 3 minus 1, or n minus 1 for the day n. So day 1, that'd be 0 here, so total of 1. Day 2, this is 1, this is 2 actually, and this is 1, so that's 3. Notice that this is just the formula for odd numbers as well. But what that tells us is that the number of widgets we're going to sell on day 20, if we plug that in here, that is going to be 19 times 2, or 38 plus 1, which is 39. And so now what we're going to try to add is 1 plus 3 plus 5, all the way to 35 plus 37 plus 39. And so what do we notice about this kind of sum? Yeah, it is an arithmetic series, but it might be very easy to sum this up just by pairing it off. Exactly as RC said, we're going to find groups. Notice that 1 plus 39 is 40, 3 plus 37 is also 40, and that's actually going to happen for every single little amount here. And because we have 20 total days, well, there's going to be 10 of these pairs of 2. So that's going to be 10 times 40 for a sum of 400. And notice that this sum of 400 was exactly the number of days we had squared. And that's not a coincidence. In fact, you can explore this later after class, but if you have odd numbers and you sum them up, the sum of the first n odd numbers is just going to be n squared. And this is very useful in general. You can prove this with a lot of different methods, but I will leave you guys for that on your own. All right, it looks like we are ready to move on. All right. And Kevin, it looks like we can't hear you. It's okay.
Now, yeah, so now we can move on to question number 10. And question number 10 is quite a simple, at least quite a simple statement. It just asks, how many integers between 1,000 and 9,999 have 4 distinct digits? And this problem is actually, it looks quite simple, but it's actually a little more complicated than it looks, because let's see here, because we have 4 different numbers, so let's see, so we have 4 blanks to put 4 digits, right? And so we can see here that the first digit cannot be 0. So any of these other digits that's not the first digit can be 0, but the first digit can't be 0. So that means there are 9 ways to choose what the first digit can be. Now after we've chosen the first digit, there's also 9 ways to choose what the second digit can be, because we can choose 0 now, but we can't choose whatever number this was because it has to be distinct. So there's 10 minus 1, which is 9 ways to choose this. Now for this one, there's 8 ways because there's 10 minus 2 ways we can choose this third digit. And finally, there are 7 ways because we can choose the last digit, because there's 10 minus 3. Since we've already chosen 3 of the digits before that. And this equals, if you do some arithmetic, 4,536. Now this strategy actually makes this problem quite simple, but it's actually not that easy, because this strategy is known as constructive counting. In short, you're looking at one digit at a time. How many ways can I choose that digit? Then I'm going to multiply it to how many ways I can choose the next digit, and so on and so forth. So the final answer is 4,536.
Yeah, that sounds correct. And actually for this problem, in the AMCs, you often don't have a lot of time, so time savers are really helpful. And when doing multiplication like this, there's actually a little bit better of strategy to just get this quickly. And so one thing let's notice, this is 9 times 9. That's going to be 81. But notice that the units digit of 81, that's 1. And that means we can ignore the tens digit for now, because we're just solving for the units digit first. and you'll see why later. But then after that 1 times 8, that becomes a units digit of 8, and then times 7, that becomes 56, or units digit of 6. And why is that important? Well, if you look at all of the answer choices, the only units digit with 6 is answer choice B, or 4536. So from there, you automatically know that it has to be that answer choice B. Exactly. There's only one 6. So this is a pretty fast way to get an answer, because really in this competition, you don't necessarily need the exact answer unless you know the correct letter choice. So those are little shortcuts that can help you. But let's move on to question number 11. Okay, it looks like we have another counting problem. So in a small country of Mathland, all license plates have 4 symbols. So 4 symbols, that's important. The first is a vowel. And then after that, we have the second and third, which have to be 2 different letters among the 21 non-vowels. That's just saying consonants. So non-vowel. And then our final symbol is going to be a digit. So again, we're going to be using our ideas of constructive counting. So we already have a lot of chat messages for how many ways for each little part. So obviously for vowels, there's 5 vowels, A, E, I, O, U. So that's 5. And then the problem itself already tells you how many non-vowels there are. So there's going to be 21 there. And then this problem does say that the 2 non-vowels are different. So for actually the second non-vowel, that's only going to have 20 possibilities. And then digits, because there's no digits before here, there's no restrictions on that. So that's just 10. And because we have a lot of nice zeros and 5s here, it's pretty nice to multiply out. What I would do is combine the 5 and 2 to get a 10. So then we have 21 followed by 3 zeros. And now let's go back to what this problem is asking for. We want the probability that the plate is going to read AMC8. What a coincidence. So if we want it to read AMC8, notice that this can only be attained in one way. There's only one unique plate that'll have this. So the successful is going to be 1 over our total of 21,000. And that is going to be answer choice B. So again, we're using constructive counting here because each of these choices are independent after we have decided the number value, so we can multiply them together and get our answer.
Yeah, absolutely. And this really just shows how important constructive counting is to solve these types of combinatorics questions where, we have a lot of different digits that actually don't really depend on each other, right? And so now I'll move on to the next problem. And hey, we're already almost halfway done. And this problem is actually question number 12, and it's a bit of a 3D geometry question. So I asked how many pairs of parallel edges, such as AB and GH or EH and FG, does a cube have? So this problem is quite tricky because we want to count how many pairs of parallel edges it has, but we don't quite know, exactly how we can count parallel edges. So I guess first it'd be helpful if we had a diagram, which I'll pull up right now. And after that, we can see that, for this question, what is a good way we can use to figure out or how many pairs of edges are going to be parallel? Does anyone know how we can figure that out? How many edges are parallel in this question? Okay, I'm seeing a lot of people type in an answer, which is actually not correct. But it's okay because so the main way we want to do this question is also I don't think counting would be a good idea either. So the main way we want to do this question is we can see here that and I think this is not the official solution, but this is the solution I just found. We can see there's edges like these, which are so these 4 edges are parallel. These 4 edges are also parallel, so I'll use a different color. So the yellow edges are all going to be parallel, and there's 4 yellow edges. And there's also going to be 4 orange edges are all parallel. So these four edges are all parallel. And then we have four other edges as well that are also parallel. So we can see here that we have, for each orientation, there's four edges that are parallel. So in other words, after we choose which orientation we have in three ways, so there's three ways to choose, which color we're going to have. And after that, we just have to choose two edges out of the four to determine which two are parallel. So it's 3 times 4 choose 2, which is going to be 3 times 6, which is going to be equal to 18, which is our final answer.
Yeah, that's a very good approach to this problem. And the biggest thing to realize here is that there's only 3 real groups here. It's going to be the horizontal, the vertical, and then the other way of looking at horizontal. So once you know that there's only 3 groups, then you can do more basically casework within each of the groups. And that can also help you use a little bit of combinatorics to help you with that. But let's move on to question number 13. And this question, we're having a set of the integers from 1 to 11, and we're looking for subsets of 2 elements that can be taken away from the set so that the average of the remaining numbers is 6. So there's a few parts to this problem. What we do know is that 2 elements are going to be taken away from the set. And then our restriction is that the remaining numbers have an average of 6. So first of all, how many numbers are currently in this set? We have 1 through 11, but how many numbers is that? Okay, RC says there are 11 numbers, and so does ANC. So because there are currently 11 numbers, once we take away those 2 elements, there's going to be 9 numbers left. And if we want those 9 numbers to have an average of 6, we know that their total is going to be 9 times 6 for a total of 54. And so one thing that's helpful is how many numbers what was the sum of the numbers in our set originally? So, okay, I see RC typed in the chat, if you add all the numbers, you get 66, which is completely correct. If you add all of these together, you get 66. Fast way to do that, pair it off like we did in the previous problem, you'll get pairs of 12. And there will be a 6 in the middle. But after you pair that up, you're going to get a sum of 66. And the reason why that's important is that we know 2 things, the sum of the original, the sum of the post removing. And what that tells us is that if we subtract those, that'll give us the sum of the 2 elements that we removed. So the 2 elements are going to have a sum of 66 minus 54, and that is just 12. And so from here, as ANC said, we're subtracting off these 12, but that's also telling us the sum of the elements we're removing. So because the problem asks how many subsets, we're basically seeing, okay, how many numbers in here are going to sum to 12? And what we did earlier is we paired off, so we knew which elements sum to 12. Basically 1, 11, 2, 10, 3, 8, and 4, 7, and 5, 6. So that's going to be 1, 11, 2, 10, okay, 2, 10, 3, 8, okay, that's actually 3, 9. And then 4, 8, and then 5, 7. So these are going to be our 5 pairs. Everyone in the chat is getting 5, which is great. And notice that because we had an odd number of numbers in this set, we're only going to have 5 pairs because our 6 is just left alone there. And so remember that these pairs, these are the same as if you arrange them 11, 1, 10, 2, etc. So these are your only 5 pairs that we have. And so our answer is going to be choice D of 5. And of course, in the beginning, I saw some people doing some guess and check based on removing certain values. And that's a great approach to start problems, but the easiest thing to do is have some sort of condition for a problem so that when you try and calculate the amount, it's not as much of a hassle because what we did is we took, okay, the two numbers have to sum to 12. And there's really only 5 ways to do that. And so from there, we can just list them off and then be done.
Yeah, definitely. And oh wow, we're almost halfway done. And finally, we have another question, which is, which of the following integers can be or cannot be written as a sum of four consecutive odd integers? So this is actually quite an interesting question. And the way we can do this is, well, we can look at, all the answer choices. And the answer choices are going to be, let's see, 16, 40, 72, 100, and 200. So when I look at this problem, what I'm thinking is that to do this problem, we'll probably have to use something known as modular arithmetic, or essentially we'll have to look at some remainders, And so, we can first of all we can just look at if we have four consecutive odd integers. Well, let's say our first integer is going to be 2k or 2k minus 3, or 2k plus 1. Next one will be 2k plus 3, then it'll be 2k plus 5, and 2k plus 7. So if we add all these up, we'll look at 8k plus 16, which is equal to 8 times k plus 2. So we can notice something here, which is that these four consecutive odd integers is going to be equal to 8 times k plus 2. And in other words, this basically has to be a multiple of 8. Now, if you look at our answer choices, all these numbers except for 100 are actually multiples of 8. So the only number that cannot be written or is not a multiple of 8 is going to be answer choice D. And so D is going to be our final answer.
Yeah, the whole idea of writing out these numbers in terms of variables is very, very useful, especially if you can factor out things like numbers to tell you what these are going to be factors of. And actually, another way you could have written this was, okay, because it's really nice to have things balance out, let's have the middle number be in the middle of everything. So over here, we could write this term as 2k minus 1. Over here, 2k plus 1. Notice that you're adding 2 to get from here. So it's still the same idea, except we're kind of shifting things around a little bit. So over here, that's 2k minus 3. And at the very right, that's 2k plus 3. And notice that when you add these all together, you're actually going to have the 1s and 3s cancel out. So our sum is just 8k, which makes it very clear that we need a multiple of 8. And then we finish off the same way as Kevin did. All right, next question, number 15. We're officially over halfway. Okay, so at Euler Middle School, again, what a coincidence of a name. There are 98 students that voted on 2 issues in a school. So 148 people voted in favor of the first, 119 in favor of the second, and then 29 students who voted against both of them. So in these questions, once you get more familiar with them, you can do them pretty quickly, but the best way to visualize it is with a Venn diagram. So this first circle is going to represent issue 1. The second circle is going to represent issue 2. One thing we know is that everything in this box is going to be a total of 198 students, because that's the students who actually voted. In this case, we're going to let the outer part of the box, which is inside the box but outside of the circles, represent the part where the students are voting against the 2. And so we know that that's going to be 29. And the only thing that we don't actually know is, well, what's in the middle? What students voted for both of them? And so what's helpful here is to create some sort of variable because we don't know it. So let's just call it X. That's a very common variable name. And what we do know is that 149 students voted in favor of the first issue. So this circle over here is 149, but if we want to adjust the left, which is the kids who voted for just issue 1, but not issue 2, that's going to be our total 1 minus x. So notice that now the circle is going to sum to 149. Similarly, over here, we take the 119 people who voted for the second issue and subtract x from that. And notice again how this sums to 119. And so what's nice about this is that when you add it up, you're going to still have the variable x, but we can set it equal to 198. And this is similar to what everyone is doing in the chat, just in a visual way to represent it. So what we can now do is add 29 plus 149 minus x plus 119 minus x, and that is going to be equal to 198. And the reason why we couldn't just add 149 and 119 right away is because there is some overlap. It could be 0, but we know because right away when you sum it, it's greater than 198, there has to be a positive overlap. So that's where the x comes in. And so now what we want to do is solve this. So what we can do here is, well, okay, these x's are going to cancel out, but there's still going to be a minus x over here. 29 plus 149 is 178. So 178 plus 119 is equal to 198. And the reason why I left it as 178 is that if you subtract it over here, that's going to give you a nice value of 20. So 119 minus x is equal to 20. And then finally, when we isolate the x, we get x is 119 minus 20, which is 99. And what's very nice about these problems is that once you get your answer, you can easily plug it in and then check that it works. In this case, we plug it back into here and check that our original problem statements were satisfied. And this is going to be answer choice D.
Yeah, absolutely. And something that's really important for this problem is just, realizing, that we want to correct for the overcount and not making that mistake of just adding the two sets independently. Now we can move on to question number 16. So we're getting to the final 10. And in this question, it says, in the middle school mentoring program, a number of the 6th graders are paired with a 9th grader student as a buddy. So no 9th graders assign more than one 6th grade buddy. So if 1/3 of all the 9th graders are paired with 2/5 of all the 6th graders, what fraction of the total number of 6th and 9th graders have a buddy? Now, something that might be helpful is, we can set two variables here. We can say that S is the number of 6th graders and N is the number of 9th graders. So we can see here that, 1/3 of all the 9th graders are paired with 2/5 of all the, 1/3 of all the 9th graders are paired with 2/5 of all the 6th graders. So 1/3 of all the 9th graders is equal to 2/5 of all the 6th graders. And, we can simplify this to get 5n equals 6s. And finally, after that, we can see that using, we want to figure out, what total percentage of 5th graders or 9th graders and 6th graders have a buddy. So the number of, so let's say, since we know that, 1/3 of the number of 9th graders have a buddy, so, so 1/3 of the number of 9th graders have a buddy, and 2/5 of all the 6th graders have a buddy. We want to divide this by n plus s. Hopefully I'm doing everything right. But one other important thing to know here is that, let's see. So one important thing we can see here is that, 1/3 of all the 9th graders plus 2/5 of all the 6th graders is going to be our total number of buddies. And S over N is going to be the total number of people. So this fraction actually tells us how many 9th graders and 9th graders and 6th graders combined have a buddy. So we just want to solve for this. However, we can see here that, 1/3 N equals 2/5 S. So the numerator rewrites as 2/3 N because, we can just write in terms of one variable. And the denominator is N plus S. But S is also equal to 5/6 N just by simplifying. So we end up getting that 2/3 N divided by, S, by 11/6 n is the total number of, is the total fraction. So this fraction is going to be equal to 2/3 divided by 11/6, which equals 12/33, or 4/11ths. And that's the total number of people we have. And the main idea here is that we can, after we get this equation, right? So after we know the fraction is going to equal 1/3 n plus 2/5 x divided by n over n plus s, we can essentially just, substitute to make sure that equals one variable, or the variable n.
Yeah, and one thing with a lot of these problems is that notice how we didn't really need to know the variable numbers. So essentially, no matter what variable numbers you have, the answer is going to be the same. And so what that tells you is, okay, if we just set a number for n and s, whatever we choose, as long as it satisfies this, it'll work. So if we choose the most minimum amount, which is saying that n is 6 and s is 5, right? Because then 5 times 6 is 6 times 5, then that will still give us our same answer because we're just having some numbers assigned to these variables. And that's still going to give us the same ratio, but it might be a little bit easier to work with. So because we knew that 1/3 of n had a buddy, because we let n equal 6, that'll be 2. For the 6th graders, 2/5 of 5 is also 2. And then our total is 6 plus 5, and that also gives us 4/11. Sometimes it just might be easier to not have as many variables. And exactly, RC, we're going to just make an example. And it's very important to understand when you can make an example. It's for problems that the answer itself doesn't change when you make an example. So for example, when you're solving for a ratio, that isn't going to change based on what numbers you have. For example, 2/4, that's 1/2. That's the same as 6/12. So whatever you chose, as long as it satisfied a requirement, you can still get the same answer in the end. So you're going to see a lot of problems like this where you can just make example numbers and I'll still give you the correct answer. And sometimes it will be a lot easier. But let's move on to problem 17. Okay, we have a rates problem. So we have Jeremy's father who drives him to school in rush hour traffic in 20 minutes. On a day that there is no traffic, his father can drive him 18 miles per hour faster and gets him to school in 12 minutes. So we want to know how far in miles is it to school? So the distance to school. So what can we do to relate distance with his speed and with the time that it takes? What is our number one equation for rates problems? And yes, SP, we will use that fact a little bit later. Exactly. Okay, distance is actually equal to rate times time. So the distance is speed times the time. That is your go-to equation for any rates problems. It'll be very, very beneficial. And so we have two scenarios here, one in rush hour traffic and one where there's no traffic. Let's consider the rush hour traffic first. In rush hour traffic, we're driving the same distance. So that distance is going to be traveled in 20 minutes with a certain speed we can still call s. And remember in this problem a little later, we were given a speed in miles per hour. And so as SP mentioned earlier, we want to actually convert our minutes to hours first. So we stay consistent with our units. So 20 minutes is also 1/3 of an hour. So this over here is going to be 1/3. So this is scenario number 1. Our second scenario is when there's no traffic. So his father is being able to drive 18 miles per hour faster, and that means he gets to school in 12 minutes. So 18 miles per hour faster. That means that we're increasing our speed, s, by 18 miles per hour. So that's going to be s plus 18. And then what is going to be 12 minutes in terms of hours? Exactly, SP. That's going to be 1/5 of an hour, or 12/60. So times 1/5. And so now we have two scenarios, each with an equation. And because we have two variables in those equations, we can solve for what we're looking for. And we wanted to find D. So the easiest thing we can do here is we can set these values equal because they're both expressions for D. And so these are our S values. So that means we have 1/3 of S is equal to, if we expand this out and multiply it out, that is 1/5 S plus 18 fifths. And so here we can solve for S. And RC asks, would finding how far you can go in 12 minutes at 18 miles per hour help? That's exactly what we're doing with this scenario here. We're setting up some sort of relationship here, but what we have to remember is that our ultimate goal is our distance. And so we want to stay as close as possible as we can to this variable D in order to get to our answer. So that starts with solving for S. What is 1/3 S minus 1/5 S? And what we can do is set up a common denominator here. And the common denominator, as SP said, is going to be 15. What is our numerator going to be then? It's going to be 2. Good job, RC. So 2/15 of S is going to be 18 fifths. So now what we can do here is solve for the speed. And that's just multiplying by 15 over 2 times 18 over 5. And that is going to be 3 times 9, or 27. And so now, what was the problem asking for? The miles it takes to get to school. So again, we're solving for D here. And we can technically choose each of these equations to solve for, but clearly the first equation is much simpler. So let's do that. So S times 1/3 is 27 times 1/3. So our answer is going to be 9. And that is answer choice D. Big thing about this problem, set up equations in terms of what you're given in the problem. And then that can give you your variables that you wanted to solve for.
Yeah, absolutely. And now we can move on to question number 18. In question number 18, we have an arithmetic sequence in which each term after the first is obtained by adding a constant to the previous term. So for example, 2, 5, 8, 11, and 14 is an arithmetic sequence with 5 terms, in which the first term is 2 and the constant 3 is added. In each row and each column in this 5 by 5 array is an arithmetic sequence with 5 terms. I want to know what the value of x is. Well, let's see. So, first of all, to start off with this problem, we can see that we can try to compute basically. Let me pull up a quick diagram. So basically the main idea here is that since, we have each row and each column is a arithmetic sequence, well, if the first term of this arithmetic sequence is 1, so we're looking at this arithmetic sequence right now. If the first term of this arithmetic sequence is 1, and the last term is 17, well, this middle term, the third term, by definition, is going to have to be equal to the average of the two, of the first term and the last term, since this is the middle term. So this is going to be 1 plus 17 over 2, which equals 9. And similarly, for this one, we have this is 25, and that this is 81. So this middle term is also going to be the average by the exact same logic. So it's going to equal 25 plus 81 over 2, which equals 53. Now finally, remember that this is also an arithmetic sequence. So which means that this middle term is going to be the average of 9 and 53. So x is going to equal 1/2 of 9 plus 53, which equals 31. And that's our final answer. Now for this question, remember, even though it looks pretty simple when I just solved it like that, it's very important that you understand very well what an arithmetic sequence is, because we can see here that we want to figure out what this term is, and we can get this information by using the first term and the last term of the sequence. Similarly, we can get the first term and the last term of the sequence here to get 53 here. Now this middle term is going to be half of, or the average of 9 and 53, which equals 31. And that's how we can solve this problem.
Yep. And notice how we really don't need too much information. You could definitely fill up this entire board with all the numbers you want, but really, let's focus on what we can do here and try to do as minimal work as possible. And that's actually really nice in this problem. And our C asks we just subtract the bigger number and the smaller number and then divide by 4 to how much we move up per step. That's exactly correct. Because, okay, if you start with 1, go to 25. We're going up by the same number each time. And so how many times are we going up? Well, to the second square once, third twice, fourth 3 times, fifth square 4 times. So 4 times that we go up means that that's going to be our difference. So 4 times we go up, each time is some variable a. That's going to be our difference, which 25 minus 1 is 24. So that a is 6. And so that's kind of how you can understand how much you go up each time intuitively. Of course, there's equations for that, but it really doesn't mean too much unless you understand how to actually get there. So that's a little bit part of this problem, but let's move on to question number 19. All right. Ooh, okay. We have a nice diagram for this question. And let's read the problem first. So we have a triangle with vertices A, B, and C plotted on a 6x5 grid. And we want to know the fraction of the grid covered by this nice green triangle. So there's actually a lot of different ways to do this problem, which makes it really nice. So let's just try something a little simpler. If we had some sort of triangle that was in here, how are we going to actually find its area? For example, if we had this little blue triangle over here. Well, that's pretty easy. That's just taking the base and height dividing by 2. But this one is a little bit slanted. So we kind of have to think outside of the triangle a little bit. And I mean that literally, and we're going to have to do some sort of expanding to do so. And what's nice about this coordinate system, it's going up by 1 each time. So it's going to be 1, 2, 3, 4, 5, and 6. And exactly as AS says, you can draw a triangle, or actually a rectangle around this green triangle. And because in math competitions like these, we value right triangles so much because of how easy they are to calculate in terms of area. And by drawing in this rectangle outside of the green triangle, we get a bunch of nice right triangles surrounding this green triangle. So my question to you guys is, what's easier to calculate? The green triangle area or the red triangle areas? Notice that the right triangles are right. Exactly. It's going to be a lot easier to calculate the red triangles. And so let's start off with the one on the bottom. What is the area of that going to be? This is just a right triangle. So looking at the coordinate system will tell you guys what the lengths are. So it might be easier if I add in some coordinate values. So this over here is D, E, and F. So what is the area of AFB? Okay, Brian says 4. Let's check that. The base FB is going to be an area of, okay, it's going to have a length of 4 on the bottom, a height of 2. And notice that the 2 just cancels out when we have to divide by 2. So that's just 4. As Brian said in the chat, notice that these brackets around the AFB mean area. And what is the area of ADC? So the red triangle in the upper left corner. We're going to use the base of DC and the height of AD. It's going to be very similar. Okay, yeah, it's 1.5 as Brian says. That's also 2 times 3 over 2. Or actually 3 times 1 over 2, which is 1.5. I'm going to leave it like that for now. Because if we look at our last triangle, BCE, it is very, very similar. Actually, we have BE as the height, but that's also the same as if we had it as the base and sort of rotate it a little bit. It's actually exactly the same as triangle ADC's area. So what we can actually do to account for that is 2 times ADC, which is 2 times 3 times 1 over 2, or 3. So this is going to be the total area of the right triangles. And so now let's do some subtraction. What is going to be the area of the green triangle? In fact, the reason why we drew the rectangle around it was so we can use a subtraction technique. So the area of this is just going to be the big rectangle minus the little. So, all right, great job, Brian. So we know that the height is 3, base is 4, so the rectangle is 12, subtract 7, you get 5 for the green area. But now, what is this problem asking for? We want the fraction of the grid covered by the triangle. Luckily, in the problem, it tells you that it's a 6 by 5 grid, so that saves you a lot of time. Exactly, Brian. So what we're doing now is we're taking this 5 and dividing it by the 6 times 5. I keep it as the 6 times 5 just so we can cancel out the 5s. And that is just going to give us 1/6. And I said in the beginning of this problem, there's actually a lot of different ways to solve it. Another way you could have used is a little bit more advanced, but it's called shoelace theorem. And if you're interested, you can check it out after class. Or after this live solve.
Yeah, definitely. And I think with that, we're going to move on to question number 20. So this question is actually quite tricky, and I thought it was quite hard actually when I was looking at it. So it says that Ralph went to the store and bought 12 pairs of socks for a total of $24. Some of the socks he bought cost $1 a pair, some of the socks he bought cost $3 a pair, and some of the socks he bought cost $4 a pair. So if he bought at least one pair of each type, how many pairs of $1 socks did Ralph buy? Well, something that might make this problem a little bit easier is we can say, let's say that A equals the number of $1 socks he bought, B equals the number of $3 socks he bought, and C equals the number of $4 socks he bought. And now what this means is that we can actually say that we can set up a system of equations, right? Because he has a total of 12 pairs of socks that they bought. So A plus B plus C is going to equal 12. But also we know that the total cost is going to be $24. So A plus 3B plus 4C equals 24. Now we can actually subtract these two equations and end up getting that 2B plus 3C equals 12. And we can also say that this equals A plus B plus C. I think I might have messed up like my cancellation a bit, but those are the two equations we get, right? And actually we can also rewrite this as we can say that since 2B plus 3C equals A plus B plus C, we get that B plus 2C equals A. So we have two equations here that we can work with. Sorry, this is bad drawing. So as long as whatever we get are both integers and satisfy these two equations, we are in business. And finally, we can end up seeing that since all these numbers have to be at least 0, I believe. Yeah, so they bought at least one pair of each type. So A, B, and C are both positive integers, at least or greater than 0. Now, since they're greater than 0, what this means is that in this equation, we can see that B is going to be greater than 0, but also C is going to be greater than 0. So what this means is that B either equals, so we can look at C, right? Since B is even, that means C is also going to be even. So that means C is either going to equal to 2 or equal to 4, because it can't be 0. But if C equals 4, then we see that 3C is going to equal 12. So B is going to equal 0, which is no bueno. So C equals 2, and then B equals 3. And finally, we want to solve for A. So we know that B plus 2C equals A. So B is 3 and 2 times C is 2 times 2, which equals 7 as A. And that's our final answer. And one important thing to know about this problem is, yeah, I see that my writing is cut up a little. I'll fix that in a bit. But the main thing to know about this problem is that we essentially want to think about this problem as, having two equations, but we have to know that these equations have to be positive integers. So basically, we can use process of elimination to figure out the system. And yeah, my writing is a little cropped, but I'll try to fix it for our next problem. Sorry about that.
It's all good. Yeah, after we have like more of a condition for problems like these, once you do a little bit of trying out some values, it's not actually too much work. All right, let's go to problem number 21. This is a geometry problem. Okay, wow, we have a nice figure here. So let's read our problem. We have a hexagon ABCDEF, which is equiangular. That means all of the angles are equal. And ABJI and FEHG are squares with areas 18 and 32 respectively. And then we also have that JBK is equilateral over here. And we also have FE is equal to BC. And so the problem wants us to find the area of KBC. So KBC, I will highlight in red, is what we want to find. So we are actually given a lot of questions or a lot of conditions in this problem. Let's just start off with the hexagon condition. If it's equiangular, what do we know about it? Well, a regular hexagon, all the sides are the same, all the angles are the same, but this is just equiangular. So that means that just the angles are the same, not necessarily the sides. So what is each angle in this hexagon going to be then? And more specifically, we want to think about the angles over here, but they're all going to be the same. So what is the total angle sum in any hexagon? It's just going to be, think of it as splitting it into 1, 2, 3, 4 triangles. Each of them is going to have an angle sum of 180, so the total angle sum is 720. So now, what we want to do is we want to find the angle sum in each angle. And really all we're just doing is dividing by 6. So each angle is going to be 120 degrees. And this is a very nice number. But let's look at to what the chat says first. So RC, Brian are talking about the lengths of BK and BC. So let's start off with this square over here. Its area is 32 and the sides are all equal. So this FE is going to be the square root of 32. That's essentially just, okay, 32 is the side squared. So to square root and give back to the side length, that's going to be square root 32. And because we are given that FE is the same as BC, can put that over here as square root 32. And similarly, JB is going to be square root 18. So BK is square root 18 because this is a equilateral triangle. And so now we had some discussion in the chat relay by RC and Brian talking about KBC being a special triangle. And that's kind of why I asked about the angle before. Notice that, okay, if we have each angle being 120, what do we know? Well, IBJ. A is a square, so that's 90. We have an equiangular or equilateral triangle, so that's going to be 60 here. And this is 120. So because this is a circle here, what is the angle of CBK? It's going to be 360 minus whatever we had else here. So what do you guys think? What is the angle actually going to be? Ooh, it looks like we have a no-name hack in the chat. Do you guys want to tell me what is the sum of 120, 90, and 60 degrees? Yeah, RC, it's going to be 90 as the difference. So if we subtracted 120 and then added 90 and 60 to that subtraction, that's going to give us 90. So we have a right triangle. We love right triangles so much. And the reason why is because, well, the areas are much nicer to calculate. And we honestly now have all we need. we have BK, we have BC. So now we can just apply what we've been doing all along. So guys, what is the area going to be of BCK now? We know square root 18 and square root 32 are the side lengths. Great job, RC. We're going to take those sides, multiply them, divide by 2 as our base times height over 2 area formula. And we notice that they're square roots, but before we take them out, let's put them all under the same square root. So it's going to be 18 times 32 all square rooted over 2. And what's nice about this? Well, 18 is 2 times 9, and 32 is 2 times 16. What do we know about 9 and 16? They're actually very special numbers. Exactly, RC, they are squares. So that means that we can take them out as 3 and 4. And notice that we have 2 extra 2's, and that's going to give us another square. So this is 3 times 4 times 2 all over 2, which is 12. And you guys did say square root 576 over 2, which is correct. But notice that if we break this problem down, we don't actually have to calculate those really big values. And again, those are the little time savers that will add up to a lot of time. One of you guys typed in the chat that you only had 2 minutes left. Imagine if you applied all these time savers to all of your problems, you might have a little bit extra time to attempt some more problems. But that's about it for this problem.
Yeah, and now we can move on to question number 22. So question number 22 says, on June 1st, a group of students is standing in rows with 15 students in each row. And on June 2nd, so they're standing with all the students in one long row. On June 3rd, the same group is standing with just one student in each row. And on June 4th, the same group is standing with 6 students in each row. So the process continues through June 12th with a different number of students per row on each day. However, on June 13th, they cannot find a new way of organizing the students. So what is the smallest possible number of students in the group? Yeah, so the way we want to look at this problem is, this kind of, might be like a bit of a combinatorics problem, but I think it actually might be a number theory problem. So this problem is actually quite tricky because we have 12 days and we have a different number of students per row on each day. And so we want to see the total numbers or the smallest possible number of students in the group. So first of all, one thing we can see here is that obviously, let's just say that hypothetically, n is the number of students in the group. So n is the number of students. Because we can arrange them in 15, so 15 students per row, that means that 15 divides n. And since we can arrange them in 6 students per row, 6 divides n. So combining these two things, we actually see that n is actually a multiple of 30 because it can be arranged, or it divides, or 15 and both 15 and 6 divide n. So 30 actually divides n. So n is a multiple of 30. And this little fancy sign this fancy line is just a way of saying that 30 divides n. And that means that n is going to be a multiple of 2 times 3 times 5. But if we just have this, we're still not quite at 12 factors, right? Because we can see here at 12 different days, we can have a different number of students per row. So what this tells us is that we have 12 factors in n. So n equals 12 factors. But right now, we only have 2 times 2 times 8 because there's 2 ways to choose the exponent for the 2, there's 2 ways for the 3, and there's 2 ways for the 5. And what this means is that we only have 8 factors here instead of 12. Now, how can we increase one more factor? Well, the way we can increase a factor is, well, we have to increase one of these exponents by one more. So let's just say we can increase the exponent of 2 because 2 is the smallest number. So if we increase the exponent of 2, we end up getting that n equals 2 squared times 3 times 5. And aha, well, this gives us 2 plus 1, which is 3, times 2, which equals 12 factors, which is what we want. And this means that n equals 2 squared times 3 times 5, which is 60, is actually the largest possible answer we can have. And this means that 60 is going to be our final answer. And so for this problem, even though this question is a combo, looks kind of like a combo question, we can actually use number theory ideas to solve it.
Yeah, those are some great ideas. And actually, a very quick way to do this problem, a lot of you guys already mentioned in the chat, just taking the smallest possible value that's divisible by, well, 15, 1, and 6. And that's definitely a valid way to do this, but to ensure our answer even more, once we do get that 60 here, what we can do is test that it does have exactly 12 factors. And the reason you can automatically see it's 12 factors is, each day is one factor. So that's going to be 12. And so if we do double check, 60 does have 12 factors. And so we can confirm it is our answer. And congratulations to RC for getting above 40 stars. Time for problem number 23. Okay, this is a pretty long problem. This is a little interesting. Let's read it step by step. So we have Tom, who has 12 slips of paper over here, and he wants to put into 5 cups labeled A, B, C, D, and E. So let's label our 5 cups over here. And what we want is that the 5 integers here are going to be consecutive and increasing. So if we had some number here in A, let's say it was 1, then this would be 2, 3, 4, and 5. But of course, we have other numbers. And they are integers, so it's going to have to be something that is like 1, 2, but not 2.5. And so we're also giving some conditions of what slips go to each cup. Notice that we are going to have multiple slips per cup. There could be just one slip in a cup, but we actually don't know exactly. So let's do some organizing. The first thing we can do is let's try to figure out what is going to be in each of the cup. So everyone in the chat, what do we know given the total slips? How can we relate that to what's going to be in each cup? And luckily, these decimals are not too bad. They're not too bad to... All right, guys. Let's try to focus on this problem a little bit more, and then we can talk about that later. But what are we going to do about these slips? Can we sum them up? How is that going to help us if we do that? Because what we do know is that all of these slips are going to go here somewhere. It's going to be here in some order, but they're all going to get in there. So because every slip is going to be contributing to this, if we are able to take the total, that's going to give us some information. So what is the total value? So the total sum we will have. And RC, we don't actually necessarily know if there's a pattern, but right now what we're trying to do is figure out any sort of more information. So as says in the chat, we can add up the sum and divide it by 5 to find the C sum. But let's explain why that works. So the total sum, if we add these together, 2 plus 2 plus 2 is 6, 2.5 plus 2.5 is 5, so that becomes 11 plus 3 is 14, plus 3 plus 3 plus 3, which is 9, 23, plus 3.5 is 26.5, 30.5, so 30.5 plus 4.5 is 35. And so, all right, we have some more explanations in the chat from HMM. He says 35. All right, here she says 35 over 5. And the reason why that's really nice is actually it is 35 as a total. And it's going to be really nice because there's only actually one way to make all of the numbers in here consecutive and increasing because they are integers. So think about it. There's can only be one way because otherwise, after you steer away from that number you want, it's going to be either too high or too low. And so as said in the chat, we want to get C first. That's just going to be the mean or the average. So C is 35 over 5, which is 7. And then what's super nice about this problem, these are consecutive integers increasing. So we already know everything in the rest of the cups. So there's going to be 5, 6, 7, 8, and 9, as says. And so now let's look at the rest of the problem, which tells us some more details about what is really in each cup. So we know that a slip with 2 goes into cup E. So a slip of 2 is going to go into this cup. We also know that the slip of 3 goes into cup B. And we also know that, actually, that's all we know about this. And we're looking for which cup the slip of 3.5 has to go with. So we want to know where this one goes. All right, so given that we know these, let's do some subtraction and see what we have after each step. So let's factor in the 3 and 2. So that means we erase 1 from this list and we erase a 2 from this list. So now what we need left is 5, 3, 7, 8, and 7. And how are we going to do that? Well, the smallest number here is 3. So let's consider that first. Notice that all of these numbers are either 2 or above. So the only way we can actually get this 3 over here is with a slip of 3. So that tells us two things. First, that tells us that we need a 3 to satisfy this, but that also tells us that the 3.5 is not going to be in cup B. So after that step, we have 5, 0, 7, 8, and 7. So what are we going to do now? Well, let's just try each of these cups individually and see, which is the strategy that is doing in the chat as well. So if we consider cup A, if 3.5 were in here, what do we get left? That's going to give us a 1.5 left. But of course, in this list above, there is no 1.5, so it's not possible to be in cup A either. How about cup C? If we subtracted 3.5, that would give us a 3.5 left, but there is no, okay, there's actually a 3.5, but we would have to get another 3.5 in addition to that, which we don't have, unfortunately. So it can't be cup C either. Let's look at cup D. Cup D, 3.5 subtracted from 8, that gives us 4.5, which is possible. So let's go on to cup E and see if that works. Again, it's a 7. Similar to the situation with cup C, it's not going to work because there's no 2 3.5s. So we can subtract that off as well. And that just leaves us with cup D. And by process of elimination, it has to work. And you can double check that later. But again, we're in the AMC 8, and we know that there has to be just one answer. So you can confidently move on from this problem. But if you do have time left over, it's very helpful to check your answer. And as for stars, they do reset after a while. So you do have to consistently type in your ideas into the chat in order to maintain your stars.
Yeah, definitely. And with that, we can move on to question number 24. And question number 24 says that, whoops. So question number 24 basically says that a baseball league consists of 2 4-team divisions. Each team plays every other team in its division and games. Each team plays every team in the other division m games with n is greater than 2m and m is greater than 4. So each team plays a 76-game schedule. So first of all, this problem is actually kind of confusing. So we want to understand what exactly is going on. Well, we can see that it might be easy to understand that. Basically, we have 3, or so it's going to play three 3 other teams in its own division and 4 teams not in its division. So for each of the 3 teams in its division, it's going to play N games. And for all the 4 teams not in its division, it's going to play M games. And so the total number of games it can play is going to be equal to 76. And what this means is that we also know one important information, which is that n is actually greater than 2m. So since we know that n is greater than 2m, let's try writing this in terms of m. So we know that 3n plus 4m is going to be greater than 6m plus 4m, or whoops, 4m. So, and this equals 10m. So we know that 76 is going to be greater than 10m. So m is at most 7. So after all this, we understand that m is at most 7. And with that information, we can essentially look at all the possibilities for m, because we know that m also has to be greater than 4. So what this means is that we also have the equation going back to the beginning. We know that 3n plus 4m is equal to 76. So if we take modulo 3, and if you guys don't know what modulo 3 is, basically if we like the remainder when this is divided by 3, it has to equal the remainder when 76 is divided by 3, which is 1. So since 3n is always going to be a multiple of 3 when divided by 3, we really just care about 4m having remainder 1 when it's divided by 3. And we can see here, we can actually write 4m as 3m plus m. And again, since m is always divisible by 3, we know that, or 3m is always divisible by 3, that means that m has to have a remainder of 1 when it's divisible by 3. So m, we can say, is going to equal 1 mod 3. And if you don't know what mod means, it essentially means that m is, when m is divided by 3, it has a remainder of 1. So since we know that m divided by 3 has a remainder of 1, and also that m is greater than 4, but less than or equal to 7, there's only one possibility that m could be. So m is equal to 7. Now finally, we want to go back to the question. We want to see, how many games does a team play within its own division? So m tells us how many games they play outside of their division. So for each of the 4 teams, they play 7 games each. So outside of their division, they play 76 minus 28, which equals 48 teams, or 48 games inside their own division, and 28 games, since we know they play outside of their division. So our final answer is going to be equal to 48. In this problem, it's very important that we have a solid knowledge of what mods are, because we can use mods to essentially restrict m to only being one number, and we can use that to solve the question.
Yeah, great job. And as always, because you are given 5 choices in the AMC 8, you can go into those choices and see which one of those really does work. Sometimes it'll work for problems, in which case it's actually very efficient to do that. Other times, not so much. But yeah, let's move on to the last question of the day. Question number 25. We are almost done for today. All right, let's look at this question. We have a geometry question. Okay, so for this question, we have 1-inch squares which are cut off from the corners of a 5-inch square. And what we're asked to do in this question is we want the square with the largest area that can fit in to the remaining space. So there's a lot of squares that we can do. We can do a square like this. That's obviously not very big. We can also do a very pretty square that looks like this. We can still see a little bit of empty space though. So what do you guys think we can do to make the area of the square a lot bigger? Because right now it's pretty big, and this will actually be pretty easy to calculate. Actually, if we look at the answer choices, the area of this square is one of the answer choices. So it could be this. But let's try to think a little bit bigger because we do have this extra space and we're not really being forced to make the square be straight up. So it could be like this as well. So let's see what we have. So we have in the chat says that you have to make it touch the very edges and the corners of the small squares. So basically, we're gonna try to have the square take up every single space. And so what I actually want to do is something like this. And my drawing skills are not too great, but as long as we have the square touching as much of the perimeter of the larger square as we can, it's going to be pretty much maximized as the area because any other time you try to rotate it, it's either going to be the same area is, for example, if you just had this and then flipped it upside down, we could get a similar square. But essentially what we want to do is realize that this is the largest square. There's really no other way to touch the corner that's different from the square. And the only other way would be to make the square smaller, in which case it would be a much smaller area, which is not what we want. So now that we've established that this kind of square is the largest as possible, how are we going to find the area of it? I mean, this side length, it's positioned in a really awkward way. But do notice that all of the answer choices are integers, which means that whatever way we try this problem, there's going to be some sort of trick to get it nicer. So these sides are going to have to be, they're not necessarily nice, but there's going to be a way to make it look nice. And so Grass the Ding Dong in the chat, which is great. This is a great method that someone called and Grass the Ding Dong bring up. So what we're going to do is we actually want to take a square in the middle. And as we were looking earlier, this square in the middle, although it doesn't have the biggest area value, it's pretty easy to calculate. And so that's probably why most people would want to draw that in the beginning. But what is really nice about that? Well, now we have triangles on the outside of it, and their area is not too bad to calculate because if we look here, this, which is the side length of the middle square, is also the base of the pink triangle. And the height of this pink triangle is going to be the side length of a purple square. So given that information, we should actually be able to calculate these nicely. And so we have to go back to the original problem. So you guys now have the very big idea of how we can finish this from here. So, okay, I just want to go back to someone called H's idea about taking the hypotenuse. That's another way to solve this problem. What's great about geometry questions is that there's like so many different ways to solve them. But in this case, the reason why we draw the square in the middle is because it seems just a lot nicer. And because we are able to actually have nice integer values to work with, it's going to be a lot easier. And so as SP said, each small triangle is going to have area 3 times 1 over 2 because remember, these are unit squares. So side length of 1, original square had side length of 5. So this over here is going to be 3. And so if we know that these are parallel, so this is also 3. And so looking at the middle square first, it's going to have an area of 3 times 3. That's our square area. And then, of course, we wanted to add on the 4 red triangles now. So 4 times the area of each of those red triangles. And as we established, the base 3 parallel to here, height is 1 parallel to the unit square in the corner. So 3 times 1 over 2 for each little triangle. And so this left-hand side is 9. A nice trick for here, 4 divide by 2 first, that's 2, and then times 3 is 6. And that'll give us a nice answer of 15. Good job, everyone. We've officially solved question number 25. Of course, RC. The biggest thing for this problem is to try to think a little bit simpler and try to think a little bit more creatively. Try to make sure your whatever square you have, try to optimize your situation. And then after you've really established a square that you can work with, try to think a little simpler of how to calculate the area. Really, there are so many ways we could have finished this problem, finding the hypotenuse as someone suggested, or even doing something a little bit different. But when it comes down to it, this way is going to be a lot easier to work with. And that's pretty much it for this live solve. Do any of you guys have questions? All right, well, it looks like if no one has any more questions, then that's pretty much it for the live solve today. Thank you everybody for coming. It was so fun.
Yeah, thank you everyone for coming. Bye bye.
Bye.